So chapter 17 is going to take a lot of what we've talked about in chapter 14, equilibrium, and apply it to solubility. So we know not all solids are soluble. Some are very soluble, some very little, and so we're going to be looking at solubility equilibria in this chapter. All right, so like I said, we learned the solubilities way back at the beginning of the class, and those are solids that will dissolve very easily in water. However, a lot of solids do not dissolve very well in water. They're slightly soluble, and a lot of things will precipitate if you mix them together in water. They can't stay dissolved. So a lot of natural processes depend on this slightly soluble salts. So we're going to look at equilibria of nearly insoluble ionic compounds. And so we'll be able to answer questions like, is something soluble? Will something precipitate? Etc. All right, so probably you don't really think about it, but we know that if we have something that's soluble and you put it in water, it dissolves. Well, even if you put something that's not very soluble in, and it keeps a precipitate or it will stay as a solid, you can't tell that actually some of it, just a very little bit of it, will actually dissolve. And so an equilibrium is set up between the solid and the ions in the saturated solution. So it's a saturated solution because not all of the solid has dissolved. It has dissolved as much as it possibly can, and usually it doesn't look like very much, but there are a few of the compounds that dissolve, and so this equilibrium is set up. And so if you look at calcium oxalate, for example, CaC2O4, here's the equilibrium that gets set up. So it's a solid, doesn't dissolve very well in water. However, a little bit of it will dissolve, and so we get the calcium ion and the oxalate ion. So then we can write an equilibrium expression. And remember that we don't include solids in our equilibrium expression. So the K value is the products just multiplied, raised to their coefficient. And they're equal to a K value, and now we're going to call it KSP because the SP stands for solubility product. So just for an example here, kidney stones are often calcium phosphate or calcium oxalate. And those little buggers can really hurt when they pass through you. The solubility product constant is just similar to a Ka for an acid or a Kc for a general equilibrium. Or Kw for water. So the solubility product is the equilibrium constant for the solubility of a slightly soluble, nearly insoluble ionic compound. So, like I said, it equals the product of the equilibrium concentrations of the ions raised to their coefficients. Each concentration raised to their coefficient. So let's write, here's lead iodide, which is another very slightly soluble salt or insoluble salt. So here's its equilibrium. PbI2 goes into water, Pb2 plus I2 negative. So how would we write the KSP expression for this equation? So the KSP is going to be equal to Pb2 plus raised to the first power because it has the coefficient for Pb is just 1, but then it's I negative squared because the coefficient of I negative is 2. So don't forget about the square, raising it to the power of the coefficient. We were really good at that in chapter 14, but then we got a little bit lazy with that in chapter 16 because acids are always ever one-to-one reaction. So make sure and go back and don't forget about raising the concentrations to the coefficients. Okay, so there's two different things that sound similar. There's the solubility product constant, which is the KSP, which is a value that is the equilibrium constant for a particular salt, and it's something that you can look up. And then there's also something called just the solubility. The solubility is just it just tells how much can dissolve. So solubility is just the quantity that dissolves to form a saturated solution. So if I said, what's the solubility of lead iodide? I just mean, what is the most that can dissolve in a particular amount of water? How much of it can dissolve? And that's the solubility. And solubility can be in grams per liter sometimes, or it can also be in moles per liter in molarity. So either one of those are just fine. And it should be easy to convert back and forth from one to the other just by using the molecular weight of the compound. Now, the solubility product, like I said, is the equilibrium constant. So that's just the KSP value. So don't get confused between solubility product constant and solubility. Now, if you know the solubility, you can calculate the KSP. And so this example will show you how to do that. All right, so a 1 liter sample of saturated calcium oxalate contains 0.0061 grams of the salt at 25 degrees. Calculate the KSP. So basically they're saying the solubility of calcium oxalate is 0.0061 grams in 1 liter, or 0.0061 grams per liter. That's the solubility. And now we want to find the KSP. So there's a few things that you have to do. The first thing we have to do is convert solubility to moles per liter. If it's not already given to you in moles per liter, we need to do that, because remember that the equilibrium expression, those brackets always mean molar concentration. So we have to convert it from grams to moles. So 0.0061 grams of calcium oxalate per liter times 1 mole per 128 grams will give us the concentration in molarity, 4.8 times 10 to the minus fifth molar. Okay, so now we can set up the ice charge. So when 4.8 times 10 to the minus fifth mole of the solid dissolves, it will form 4.8 times 10 to the minus fifth moles of each ion. And this is because it's a 1-to-1 ratio in this case. So be really careful with your coefficients. But if we set up the ice chart, we can see that when calcium carbonate, if the solubility is 4.8 times 10 to the minus fifth moles per liter, that's how many of the calcium oxalate will break up. That's how much of the calcium there will be in solution. That's how much of the oxalate there will be in solution. So you can see that our equilibrium amounts are 4.8 times 10 to the minus fifth for both calcium and oxalate. So if we plug those into our expression, we can find the KSP, which is 2.3 times 10 to the minus ninth. So again, the difference, the solubility is that 0.0061 grams can dissolve in 1 liter. The KSP for this salt is 2.3 times 10 to the minus ninth. Here's another example. So just paying attention to coefficients. All right, so by experiment, it's found that 1.2 times 10 to the third moles per liter of lead iodide can dissolve in water. So 1.2 times 10 to the minus 3 moles per 1 liter of water. What is the KSP at this temperature? Again, set up your ice chart. The solubility is 1.2 times 10 to the minus third. That's how much of the solid can break up. Now, when it breaks up, we get 1 lead and 2 iodide. So keep in mind that your the iodine concentration will be twice that of the solubility. So when we set up the ice chart, you can see that the lead will be 1.2 times 10 to the minus 3 molar, but the I will be 2 times 1.2 times 10 to the minus 3 molar. Then also when you plug this into your equation, be really careful that you don't forget to square it. So 1.2 times 10 to the minus third times the quantity, 2 times 1.2 times 10 to the minus third quantity squared. And that'll give you a KSP of 6.9 times 10 to the minus ninth. Okay, so that's how you can find the KSP. You can look up solubility product constants for many ionic compounds. So most of the time the problems will involve using the solubility product constant, in which case you need to look it up. But note that the smaller the KSP is, the less soluble the compound is. So the smaller the KSP, the more insoluble it is. Now, once you know the solubility product, you can actually calculate the solubility of the compound. So you can go back and forth. So we'll do an example of that in a minute. All right, so here's some solubility product constants. And you can see, so something like aluminum hydroxide, 4.6 times 10 to the minus 33, is much, much, much less soluble than barium chromate or barium fluoride, or even barium sulfate. So you can see the smaller the number, which means the bigger the negative exponent, the less soluble it is. Okay, so now what we're going to do is to calculate the solubility from the KSP. So just like all of our equilibrium problems that we've done so far, there's one, you'll either know something about the equilibrium concentrations, which is X. You'll either know that and be able to find the K value, or you are given the K value and you can find something about the equilibrium concentrations, or X. And so the last two examples where we found the KSP, we were given the equilibrium values, or we were told what X was, and so we could find KSP. Now we're going to be given KSP and we need to find out what X is, basically. So the mineral fluorite is calcium fluoride, CaF2. Calculate the solubility in grams per liter of calcium fluoride from the KSP. Okay, so again, let X be the molar solubility of calcium fluoride. That's what we're trying to find. How much, basically, of the calcium fluoride will dissolve. Sometimes on my ice chart, I like to put a minus X under the calcium fluoride as well, because we know that that's what's breaking up. It doesn't get included in our expression, so sometimes it's not put there, but I like to put it there sometimes just to remind myself. That's what we're trying to find, how much of the calcium fluoride is going to break up. But it is important then to note that if for every one calcium fluoride that breaks up, we get one calcium ion and two fluoride ions. So if X breaks apart, we get X calcium and 2X fluoride. All right, now we can substitute it into our equilibrium constant equation. So we know that calcium is X, we know that fluorine is 2X, so, and we know that KSP is 3.4 times 10 to the minus 11th. So X times quantity 2X squared, again be careful with your math, equals 3.4 times 10 to the minus 11th. So 4X cubed equals 3.4 times 10 to the minus 11th. So if we first divide by 4 and then take the cube root, so divide by 4 and then take the cube root, we get a value 2 times 10 to the minus 4th. Well, keep in mind, you're not done yet. That would be in units of molarity. So what is the solubility in moles per liter? 2.0 times 10 to the minus 4 moles per liter. So solubility 2.0 times 10 to the minus 4 moles per liter. If we want to know in grams per liter, we just have to multiply by the molecular weight. 78.1 grams per mole gives us 1.6 times 10 to the minus 2 grams per liter is how much you can dissolve. So you can dissolve 0.016 grams in 1 liter of water. And that's how you do calculate the solubility if you know the KSP. Again, you're either going to know one or the other, and you're going to solve your equilibrium expression. All right, now sometimes, what if you have a common ion? So very similar to acid common ion problems, we're going to have a similar thing that can happen if you have one particular ion present from another source. So we're going to look at what is the solubility of some salt if one of the ions is already present. Um, again, so it doesn't really matter if the ion is something else, but we're particularly looking at what if one of the ions that's already present is one of the ions that is in the salt that we're looking at. So for example, you want to know the solubility of calcium oxalate. What is the solubility if you have a solution of calcium chloride? So you already have calcium present in the in your solution, calcium chloride, and then you're adding calcium oxalate. What will the solubility be? And if you remember what happened with the acids, well, if you have a common ion on the product side, it shifts equilibrium to the left, which means that for an acid, the acid, less of it dissociated, which made the pH higher. Well, the same thing's going to happen. Less of our solid will dissociate, and so it will be less soluble. The solubility will go down in this case. So, yep, each salt contains the same cation, and so it will be less soluble than it would be in pure water. So let's look at that. What is the molar solubility of calcium oxalate in 0.15 molar calcium chloride? The KSP for calcium oxalate, 2.3 times 10 to the minus 9th. All right, so if we set up our ice chart, note that the calcium that's already present is 0.15 because before equilibrium even gets established, we already have 0.15 molar calcium from the calcium chloride. The amount of oxalate is 0 before equilibrium. We know that some of the calcium oxalate will dissolve, so the change would be minus X under calcium oxalate. And then we're getting 1 calcium and 1 oxalate, or X and X. So calcium at the end will be 0.15 plus whatever dissolves, and the oxalate will be the amount that dissolves, X. So again, we can plug this into our equation. Calcium times oxalate gives us KSP. The KSP is 2.3 times 10 to the minus 9th. Calcium is 0.15 plus X times X. So we can solve the quadratic equation. We would have 0.15x plus x squared equals 2.3 times 10 to the minus 9th, and that would be a perfectly good thing to do. Or we can assume that x is going to be very small compared to 0.15. So here's solving for x. Again, we're going to assume that x is going to be very small compared to 0.15. There's no real test like we had with the acids where you can plug things in, but just the fact that these KSP values are so small, we'll see what happens. So we can just say, well, let's see, I think x is going to be very small, and solve the problem and then see if it really is or not. So we expect x to be very negligible, so we're going to drop that x. So x is going to be 2.3 times 10 to the minus 9th divided by 0.15. In fact, it's 1.5 times 10 to the minus 8, which is, again, very, very small, so it is very negligible compared to 0.15, so that assumption was valid. So what is the molar solubility of calcium oxalate in 0.15 calcium chloride? It's 1.5 times 10 to the minus 8 molar. 1.5 times 10 to the minus 8 molar. And if you remember, or if we did the calculation in pure water, the molarity was 4.8 times 10 to the minus 5th molar. Notice that that's 3,000 times greater in pure water than it is in calcium chloride. So that common ion will make the solubility much less. All right, so now we can switch it around. Precipitation is just the reverse of looking at solubility. So if you say, okay, how much of that will dissolve? On the reverse side, we're going to say, well, if you put this much in there, will it stay dissolved or will it precipitate? So we're going to be looking at precipitation reactions will be on the flip side of solubility. So basically going to be asking, will precipitation occur if we have a particular ion concentration? So the easiest way to do it is to go back, we did this back in chapter 14, is to look at our reaction quotient Q. So you can remember, let's see, so we can set that up, and the Q, we can predict in which direction the reaction will go if you compare Q with K. So Q is just the same thing as K, where you plug the numbers in that you have and you want to see, are we at equilibrium or not? So the Q equation is going to be the same as the KSP expression, except the concentrations are starting value or initial values rather than equilibrium values. So let's consider lead chloride. So here's our lead chloride, and we can still always put the equilibrium with the solid on the left and the ions on the right. It doesn't matter which way you do that. Even though we're looking at it from the flip side, we always write the equilibrium in this manner. So the QC expression would be Pb2 plus I initial times Cl squared I. Again, initial concentration is I. So if we're given some values, we can plug them in and see how they compare to K. So if QC is bigger than K, so Q, to get to equilibrium, Q will have to get smaller, which means it's going to have to shift to the left, which means precipitation will occur. If Q is less than K, in order to get to equilibrium, Q is going to have to get bigger, which means it's going to go to the right, which means that more solute can dissolve. And of course, if Q equals K, that is the exact saturation point, and that would be the point where precipitation would just start to occur, which is a sort of an important point that we can look for. All right, so let's look at an example. The concentration of calcium ion in blood plasma is 0.0025 molar. If the concentration of oxalate ion is 1 times 10 to the minus 7th molar, do you expect calcium oxalate to precipitate? Or in other words, will you get some kidney stones? The KSP for calcium oxalate is 2.3 times 10 to the minus 9th. All right, so the precipitation reaction that we're looking at is the calcium oxalate. So CaC2O4 dissolving into Ca2 plus C2O4 negative 2. So we can write the ion product quotient, QC equals calcium ion initial times oxalate ion initial. So we know our initial concentrations, what we're trying to figure out, will it precipitate or not? So we can plug those values in. So 0.0025 times 1 times 10 to the minus 7th. And we get a value of 2.5 times 10 to the minus 10th. So the question is, will calcium oxalate precipitate? So since Q is less than KSP, then we expect precipitation would not occur and more oxalate can stay in solution. We can actually dissolve a little bit more than what is already there. There are some other types of problems of this kind, and notice that this problem, they give you the exact molarity. So I just want you to be careful if you see other problems where they say we're going to mix 20 milliliters of this and 30 milliliters of that and will a precipitate occur. You basically do the problem the same way, except if you're mixing say 20 milliliters of 0.5 molar calcium and 30 milliliters of 0.25 oxalate, what you're going to have to do is you're going to have to figure out how many moles of each of those you have, and then you're going to have to divide again to find the concentration once you know the total volume. So you would take the concentration times volume to get moles, and then you would divide by the total volume, which in that case would be 50 milliliters, to get the new concentration. So keep in mind that if you get a problem like that where they give you volumes and concentrations, you're going to have to refigure out the new concentration in the new volume by finding moles and then dividing by the total volume. Once you have that, you can plug them into the concentrations and find out if a precipitate will occur or not. Okay, so sometimes we have to look at other reactions that might affect a solubility reaction. So for example, we know that if we have a weak acid, the conjugate base will be somewhat basic. It will react with acids or with water in an acid-base reaction. And so if the salt happens to have conjugate of a weak acid, then it will be affected by acids or bases. And so we would expect the pH would definitely affect the solubility of that particular salt. So calcium oxalate is an example. C2O4 negative 2 oxalate ion is the conjugate of a weak acid. C2O4 negative 2, if it has acid around it, will react to form HC2O4 negative. All right, so it is affected by acid. So according to Le Chatelier's principle, if you're in an acidic solution, you're going to be removing the C2O4 negative 2 by a side reaction. So that means that the reaction will proceed to the right, which means that it will dissolve more of the calcium oxalate, and so it will be more soluble at lower pHs when there's acid around. So we expect calcium oxalate to be more soluble in acidic solutions than in pure water. And that just happens to be because the oxalate reacts with acid. So limestone caves are actually, this is one of the things, limestone caves are calcium carbonate. And if they're somewhat acidic groundwater will dissolve the calcium carbonate, and then it'll form these stalactites and stalagmites. And then if the carbonate, if the carbonate kind of gets removed because of the CO2 will remove, then it will precipitate, the calcium carbonate will precipitate again, and forming, so they'll be solid again. So it's this kind of a solubility, non-solubility type of reaction that's going on, and it's because it's affected by the acidity. And once the CO2 evaporates, it's not acidic anymore, and so it will reprecipitate. So there are some metal ions that don't necessarily make solid precipitates, but actually can react with other ions in solution to change colors, or to be a little bit different from just the original metal ion. So what they do is they can coordinate covalent bonds with molecules or other anions that have lone pairs of electrons. It's really a Lewis acid-base reaction, like we talked about in chapter 15, but the main thing is that you're going to see a color change. And the reason why I bring this up is because one of the labs that we're going to do will have some complex ions, and in fact the equilibrium lab also has some complex ions. So for example, copper ion, when it's all by itself, is kind of a pale light blue. But if you put ammonia in there, which is what we did in one of the labs, lab I4, which is Le Chatelier's principal lab. If you put it with ammonia, what happens is the ammonia coordinate with the copper. The copper doesn't have any ions around it, but the ammonia, 4 of them can coordinate with the copper to make this ion, which is called a complex. Copper with 4 NH3s, but it's still 2+. So it's not a precipitate, but it forms what we call a complex ion. And that one actually turns a real bright royal blue, if you remember that lab. So it goes from a real pale blue. Actually, what happens is there's a little side reaction where the NH3 forms hydroxide, and it makes kind of a cloudy precipitate. Calcium hydroxide, copper hydroxide makes sort of a pale precipitate, but then the more NH3 you have, the more this coordination complex ion will, and you'll have that bright blue clear solution. So it's still ionic, and so it's clear. You can see through it. It's not cloudy, but it is no longer just copper ion. Here, this is what I was talking about. So when you take copper and you add some ammonia, the first thing that happens is you get kind of a light blue precipitate. But the more ammonia you add, you end up with this royal blue complex. And this is sort of a picture of what it looks like. So again, the complex ion is an ion formed from a metal ion with a Lewis base. So things like water, like OH can attach, or NH3, or even waters, and they form this sort of coordinate covalent bond. So a complex is a compound that has complex ions. So another category of precipitates is something called an amphoteric hydroxide, which is just a metal hydroxide that can react with both acids and bases. So an example is zinc hydroxide. And this kind of makes sense because you think, well, zinc hydroxide is a base, so it should be able to react with an acid. And in fact, there's a little bit of a typo here. There should be a 2 in front of the H3O plus to make that balance. But two acids will, each acid will pull a hydroxide off of a zinc. And so then we form the zinc ion and water. So this sort of makes sense because the hydroxide reacts with the H plus to give us water. However, even if a base is around, so this is similar to what we saw before, if there's a base around, what happens is that the zinc hydroxide can actually attach more hydroxide groups onto it and form an ion. So it'll make a zinc with 4 OH groups and a -2 ion, which because it's ionic is dissolved, and so it will actually dissolve the zinc hydroxide in a basic solution as well. So if you have some zinc chloride, which is soluble, and then you add some hydroxide to it, the first thing that happens is that it will precipitate. And we saw the similar thing with copper. So the first thing is that zinc will react with the hydroxides to form this zinc hydroxide solid. If you keep adding hydroxide, more and more of it will, the solution will end up dissolving and become clear and colorless. Some other hydroxides are aluminum, chromium, lead, tin, both tin 2 and tin 4. They work in a similar way. Okay, finally, the last thing I wanted to talk about in chapter 17. So notice that this PowerPoint didn't include everything that was in the chapter. So if I didn't talk about it in the PowerPoint, you don't need to worry about it in the chapter. There's some fractional precipitation and things like that that we won't get into. And we're not going to get into any calculations with complex ions. So quantitative analysis is just a way of determining the identity of what you have in a mixture. Qualitative, as opposed to quantitative, where you want to know how much of something you have. Qualitative is just identifying. And so one of the labs that you're going to do this semester will involve qualitative analysis. And so there's a way to detect the presence of a particular ion by a characteristic precipitate. Now, just keep in mind when you make a precipitate, then you have a clear liquid above it. That's called a supernatant. So you have a precipitant and a supernatant. And then what we're going to do is separate them. So you get a precipitate, you shake it up, you get the precipitate. You could separate that out by centrifuge, and you can pour the liquid off and save it, and then pour the precipitate off and save it, and you've separated them. So the next slide kind of shows what's going to happen, and you'll learn a little bit more about this in lab by doing unknowns, figuring out what ions are in your unknown. So if we have a mixture of metal ions, and let's say we add a little bit of dilute HCl, well, if most of the ions will stay in solution because they don't react with chloride, but silver, mercury, and lead do precipitate with HCl. So if you put some HCl in and you get a precipitate, then you have a pretty good chance that you have silver, mercury, or lead in your sample. So then what you can do, and you can see on the left would be precipitate, on the right would be supernatant. What you can do is separate them out and then just take the supernatant or the filtrate of the soluble metal chloride. So save the precipitate and then just take the supernatant and move on with it. There are actually other techniques now. If you want to know, is it specifically silver, lead, or mercury, you can actually do some other tests on that precipitate to figure out exactly which ones you have, but that'll be a detail that we'll talk more about in lab. So now take that filtrate of soluble metal chlorides, which have all these others, anything but silver, lead, and mercury, and now add a little bit of H2S in 0.3 molar acid. So what's going to happen? Well, a lot of the metals will still stay dissolved because they don't react with the sulfide, but arsenic, bismuth, cadmium, copper, mercury, well, of course mercury, lead, and silver are already gone, but tin and antimony will precipitate. So again, only certain ones will precipitate, so we're going to continue on. So then if we take our take the supernatant after that separation and add H2S in dilute ammonia, then some more different ions will precipitate. But some of them still won't, and so we keep going through this, and eventually you've got different precipitates that happen along the line. So I think I have a little bit better, like hopefully we wouldn't have all these metals at once. You may, in lab, you may have like a possibility of 5 metals, and so there's different scenarios that you can go through. So let's suppose you have a solution that might contain silver, copper, zinc, calcium, and sodium, and you want to determine which are present. So what you would do is you would start by adding dilute HCl. If a precipitate forms in that first set, if you go through that chart on the previous slide, the only one of those 5 that will precipitate with dilute HCl is silver. So if you get a precipitate, you know you have some silver. So then what you could do is you separate the precipitate. The precipitate will remove the silver from solution. So if you filter that off, the liquid that you have will now possibly only have copper, zinc, calcium, and sodium. So what would you do next? You would add the H2S in 0.3 molar acid. Now, which one of those would precipitate? If a precipitate forms at this point, then you can be sure you have copper, because copper is the only one of those 4 ions that will precipitate in that solution. So again, you can remove the solid and then continue to test the solution. So then you would try the H2S and NH3. H2S and NH3. If a precipitate forms in this step, then that means you have zinc in your solution. So again, now you can remove that precipitate and continue testing the supernatant. Add the NH4-2CO3 to the solution. If a precipitate forms at this point, then you know you have calcium. If it doesn't precipitate, you don't have calcium. Once you remove that, the only possible ion that might be present is sodium, and unfortunately we can't ever precipitate sodium because if we remember our solubility rules, sodium will never precipitate, but there are other ways to test for sodium by using a flame test or something like that. So anyway, you're going to do something similar to this in lab, which is the reason why I put it in this slideshow. So like I said, sometimes more than one ion might precipitate with a particular reagent, like silver and lead might both precipitate out. If we added the HCl, both ions would precipitate, but how do we know if we just have one or both of them? They can be further analyzed with more tests. So as you'll see in lab, actually, if you heat up the silver chloride and the lead chloride, one of them will dissolve and one of them won't. So once you've separated them and you know you only have 1 or 2 of them, you can do these further tests to see if they will dissolve in hot water and so forth. So like I said, if we heat up the precipitate, any lead chloride will dissolve, but silver chloride would not. So if the precipitate remains, you know you have silver, and then actually you can further test the supernatant to see if lead is present. So there are different ways of doing it. It's not just 1 and 1, but this is the idea of what you're going to be doing in lab. All right, so what should you be able to do in chapter 17? Mainly those last few won't be on the test, but you will use those in lab. You should be able to write the solubility product expression. You should be able to calculate the KSP if you know the solubility, or calculate the solubility if you know the KSP. You should be able to calculate the solubility of a slightly soluble salt if you have a common ion. And then you should be able to predict whether a precipitation will occur. And then determine just qualitative, so you don't need to do any calculations, but just determine how the pH will affect solubility. So if there's a negative ion that is the conjugate base of a weak acid, then pH will it will make it more soluble.